3.2, Rolle's theorem and mean value theorem. So, oops, went too far. Rolle's theorem. Rolle's theorem says let f be continuous on the closed interval ab and differentiable on the open interval ab. If f of a equals f of b, then there is at least one number, which we're going to call c, in the open interval, such that f prime of c equals 0. Okay, so let me translate that to English. If I have two different spots on the graph that are the same height, and these two spots happen to be the endpoints, right? So if you look at the picture, here's A. So f of A would be the y value, right? That's how tall the height is, or that's how tall the graph is. That is the height of the graph there. And then f of B, so here's B. So f of B is the y value at x equals b. Now these are the endpoints. Okay, it's important that you realize these are the endpoints. Now they're saying that if my endpoints are basically the same y value, then there is another x somewhere in between a and b, and that's what we're referring to as c. And it's anywhere. It could be here, 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 right? Just that in this particular graph, C is located where it's located because that's how they drew it. But it could be anywhere between A and B. There is an x value where the derivative, or slope, right? Slope, derivative, same thing. Where the derivative is equal to 0, or rather the slope of this point on the graph is 0. So if you look, here's the y value, and this is a maximum, right, in this particular picture. And since it is the maximum, the slope is 0. Okay, now, why is this significant? Because the slope is the same slope as if we were to find the slope of f of a and f of b. Because from this point to this point, the slope is just a horizontal line, and that has a slope of 0. So at C, we also have a slope of 0. So really, if I were to take f of a and f of b, and I were to find their slopes, it should be the same exact thing as the slope at C. But remember, if I have 2 points, I can do slope. I can do the slope formula that you learned back in Algebra 1. But if I only have 1 point, like C, then we do the instantaneous slope, which is the derivative. So here we go. Now, the whole point about Rolle's theorem is that the slope is 0. So what this is saying is there is an x value between a and b that we're going to call c. There is an x value called c that the slope is 0. Okay. In order for Rolle's theorem to be applied, the function has to be continuous on the closed interval and differentiable on the open interval. And of course, the y values of my endpoints have to be the same. So let's see, example 1. Determine whether Rolle's theorem can be applied to f of x equals sine 3x. On the closed interval from 0 to pi over 3, if Rolle's theorem can be applied, find all the values of c in the open interval from 0 to pi over 3 such that f prime of c equals 0. Okay, first of all, take note. This is a trigonometric function. And because it is a trigonometric function, sine and cosine, they are continuous. They are always continuous. Okay, just a simple sine, cosine, continuous. Right. Now, as far as differentiability, sine 3x is differentiable. Okay? So that takes care of the first two bullets. Now, the third bullet, oops. Okay, so that takes care of the first two bullets. The third bullet is f of a has to equal f of b. So f of 0, so let's see, sine of 3 times 0 is 0, and sine of 0 is 0, has to equal f of b, which happens to be pi over 3. So let's see, sine of 3 times pi over 3 is basically the sine of pi. And the y-coordinate at pi is 0. So are they equal? Yes. Yes, they are. So that takes care of our third bullet. Right? So check, check, and check. Alright, so Rolle's theorem can be applied. Now that we know that it can be applied, then we're going to now actually figure out what this c value is. That the Rolle's theorem is telling me is going to be this slope of 0. Can't talk. Oh my goodness. Okay, so what you do is you take the derivative of the function and you set it equal to 0, just like this. So sine of 3x, right, derivative of that is cosine 3x times 3, right? Because 3x is a u, and so times du. Alright, so here's my function's derivative. So now I take the derivative and I set it equal to 0, and I solve for x. Because x is my c value, right? I'm just trying to figure out what it is. Okay, divide both sides by 3. Right? Oops, okay. 0 divided by 3 is still 0, so that's not anything special there. So you would most likely do this with a calculator. At least for right now we are. So 3x is going to equal the cosine inverse of 0, which basically means at what angle, in radians of course, at what angle is cosine equal to 0? So cosine is the x-coordinate. The x-coordinate of what angle is 0? So let's see. I know that at pi over 2, it's 0. And at 3 pi over 2. And there's no other places. Okay. So let's see. Divide by 3 because of the 3x. Oops, too far, too far. So divide by 3. Right? Divide this by 3, divide this by 3. So we got x equals. Now, pi over 2 divided by 3 is the same as saying pi over 2 times 1/3, so pi over 6. And then same here, this is pi over 2. Right, did I do that there? 1/3, the 3's cancel out. Yeah. Okay, so here are my values. Now, are they within my interval? So let's see. The interval was from 0 to pi over 3. Okay. So pi over 3 is 60 degrees, and pi over 2 is 90 degrees. So, this no bueno. So this my answer. Okay? The derivative is, or rather the slope is 0 at pi over 6. Okay, mean value theorem, or MVT. If f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists a number c, again, back to this x value that we're calling c, within the open interval, such that f prime of c equals f of b minus f of a over b minus a. Now, this should look super familiar because I just did it a couple minutes ago. Actually, let me go back. her. Now, the difference between mean value theorem and Rolle's theorem is that the Rolle's theorem is specifically saying that the slope part, this part right here, is supposed to be 0. So for, what's this called? Rolle's theorem, this is basically what we're focusing on. Mean value theorem, it's not 0. Okay, this can actually equal something. And this is just saying that the derivative at this so-called x point is the same as the slope of the two endpoints. So I repeat, Rolle's theorem, it equals 0. So the derivative equals 0. And so did the slope of the endpoints. So they both equal 0. MVT, the slope of the endpoints equals some number, and it's just saying that somewhere else within the open interval, there's another x where the slope is the same. That's all it's saying. All right, so we need the function to be continuous, we need it to be differentiable, and we need our c value, which is x, to be in our interval. Now look at the picture. Okay, so endpoint A, endpoint B. Find the slope, right? Straight line connecting them, because this is just how you find slope with the 2 points, right? Now, they're saying that that slope is the same as the slope at a certain point that we are calling C, right? But it's just a single point, so when it's a single point, it's the derivative. So basically, the derivative somewhere within the open interval of some point, the derivative is equal to the average velocity, right? The regular way we find rate, a over b, or a and b. Okay, I want to point out this is the tangent line, right? The one that you're always writing equations for. It's a line that's tangent to the curve, so it's basically touching it at a certain point, and the slope of the tangent line is the same as the slope at that point. So this tangent line has the same slope as this blue dot does, right? At that instant right there. Now, this other line, from the one formed from A to B, this is referred to as the secant line. So secant line is when you find slope by using the good old-fashioned y2 minus y1 over x2 minus x1. Tangent line is when you find slope by doing the newer derivative, deriving. Okay, example 2. Analyze the following graphs and determine if the MVT can be applied. Okay, so can the mean value theorem be applied? So, is the function continuous? Yes, check. Right? Now, is the function differentiable? If you look closely, this right here, this is called a cusp. No bueno. It's not differentiable there. Okay, can't have a derivative at a cusp. Alright, so I don't even have to go any further. MVT cannot be applied. No. B. Okay, is this continuous? Oh, but right there. Point discontinuity. Not continuous. Therefore, no. C. Is the function continuous? Yes, it is continuous. Oui. Is it differentiable? Yes. There aren't any problems as far as differentiability. Now, is C within A and B? So, taking a rough sketch of this, people, okay, let's pretend I'm going to make a line here. Let's pretend, okay, so from here to here, right, there's my slope. So, could there be somewhere in between A and B that my slope is the same? And I pretty much think so. See right here? Is it safe for me to assume or say, not assume, but could I get away with saying that the slope at that point is the same as the slope from A to B? I'm going to go with yes. C is an element. Ooh, that looks like foreign money symbols. C is an element of my open interval. So, yes, it can be applied. All right, example 3. Here I have a function. Find all the values of C in the open interval from 1 to 4 such that the derivative at that point, C, right, is equal to the slope of the secant. So basically, figure out what my x value is that makes the slope of the secant equal to the slope of the tangent. All right, so very quickly, let's see. Derive. So let's actually derive this. 5 is 0, and then let me go ahead and rewrite this. 5 minus 4 x to negative 1. All right, so let me derive it. So 0, negative 1 times negative 4 is positive 4, and then x stays, and then negative 1 is now negative 2, which basically means this. So here's my derivative. My derivative needs to equal f of 4 minus f of 1 over 4 minus 1. Okay, so this stays like this. F of 4 is what I would actually get when I plug in 4 to my function. So 5 minus 4 over 4, which is 5 minus 1, which is 4. 4 minus 1 on the bottom is 3. Okay. Now f of 1, plug in 1, so 5 minus 4 over 1, so 1. So let's see, 4 x squared. All right. 4 minus 1 is 3. 3 over 3 is 1. I'm going to write it like this. If I want to solve this, I'm just going to have to cross multiply. Doing my cross products here. So 4 times 1 is 4. 1 times x squared. Square root both sides, right? Doo-doo. And I get x equals either positive or negative 2. Okay, so looking back at my interval was from 1 to 4. So 1 to 4, let's see. Positive and negative 2? Well, one of them is not in between 1 to 4. So that means my answer, my final answer, right, is just positive 2. And this is my C value, where the slope of the tangent is equal to the slope of the secant. All right, example 4. Determine whether the mean value theorem can be applied. So if yes, then find all the values of C such that the tangent line through C is parallel to the secant line joining the points. Okay, so this is basically what oops, I thought it was in highlighter mode. This is basically what I've been saying, right? And the whole parallel I have not said. But parallel just means same slope. Okay, that translates very simply as having the same slope, because that's what parallel lines have in common. Now, if you go back, or oh no, it was right here. Right here. See right here? Don't these kind of look parallel? Okay, so that's the point. So basically, number 4 is asking the same as number 3, but it's worded differently. So step 1, continuous. Well, this is a polynomial function, and all polynomial functions are continuous. It is differentiable. There's nowhere that that's going to give me a problem. So basically now I need to make sure that C is actually within my interval. But first I have to find C, and then make sure it's in the interval afterwards. So step 1. Let's go ahead and derive this baby. So the derivative of my function is 2x minus 1. Now that needs to equal the slope of the secant line. Okay, so 2x minus 1 is the slope of the tangent. And now what I'm going to find is the slope of the secant line. So we're going to do slope good old-fashioned way. So let's do 0 minus negative 6. And then 4 minus negative 2. And so I get 2x minus 1 equals 6 over 6, which is 1. Beautiful. I can move over the negative 1 by adding it. Divide by 2. And x is 1. Now, last step, very important, is this x value actually within my interval, and 1 is in between negative 2 and 4. So there it is. My c value is 1. Example 5. Okay, so these are just kind of like thinking questions. 2 stationary patrol cars equipped with radar are 5 miles apart on a highway with a speed limit of 70 miles per hour. As a truck passes the first patrol car, its speed is clocked at 55 miles per hour. So he's going well below the speed limit. 4 minutes later, when the truck passes the second patrol car, its speed is clocked at 50 miles per hour. Even less, right? Slower than the speed limit. The trucker was issued a speeding ticket. Okay, why? So he was clocked twice, both times going under the speed limit, but he was ticketed anyway. Well, let's figure out his rate. Remember, rate is distance over time. So his rate is just another way of saying slope, by the way. Of course, you could do this doing the slope way. Let's see. He was going 55 the first time. Okay, so he traveled 5 miles, right? From between patrol car 1 to patrol car 2, that was 5 miles. So from 0 to 5 miles. Now, the first time around, it was 55. And then the second time around, it was 50. Oops. Now, from when he started, let's see, from the first patrol car to the second patrol car, it took him how long to get there? 4 minutes later. So you can say 0. So 0 minutes and then to 4 minutes. Okay, so 4 minus 0 and goodbye. Oh, I put that in the wrong place. Miles. Alright, now the negative is just because it appears to have slowed down, right? So don't worry about the negative too much. Miles per minute isn't going to work for us here. We have hours. So 60 minutes. 1 hour. 300. I know it's negative. It really doesn't work good. 375 miles per hour. Okay. So according to slope, right, good old-fashioned slope, he was going 75 miles per hour, which is over the speeding limit there. I was going to do rate equals distance over time. So the distance was 5 miles total. The time was 4 minutes. Again, got to get rid of the minutes. So I've done the same thing. I skipped like this part, right? So it's still 300 over 4, which is basically 75 miles per hour. Now, that just shows me that the trucker was, at some point, right, going 75 miles per hour. Because somewhere in between 0 and 4 minutes, and I'm just going to make like a little weird graph, just so somewhere between 0 and 4 minutes shows uh, 0 and 4 minutes. Somewhere between here, the slope is the same as the slope from 0 to 4. So basically, we find that the place, right, where the slopes are the same. Now, if these are the slope, if this is the slope of my endpoints, then that means somewhere in between 0 and 4, there's another place where this same slope occurred. So at some point, these trucks were going, or this truck, sorry, was going 75 miles per hour between between the beginning to the end of the 4 minutes. And that is why the truck driver got a ticket. Okay, I'm not going to write it out, but this would be the answer. The trucker's average velocity was 75 miles per hour. By the mean value theorem, there was at least one instance where the trucker was traveling at 75 miles per hour, which is over the speed limit of 70 miles per hour. Okay, so by the mean value theorem, somewhere between 0 and 4 minutes, that trucker was driving or traveling at 75 miles per hour. The next one is basically the same idea. Plane begins its takeoff at 2 p.m. on a 2,500 mile flight. After 5.5 hours, the plane arrives at its destination. Explain why there are at least 2 times during the flight when the speed of the plane is 400 miles per hour. Okay, again, I'd rather just do rate because it's a lot faster. So the distance, let's see, it was 2,500 miles per hour. I'm sorry, miles. And the time was 5.5. So do the math here, and our rate is 454.545 miles per hour. Now, it says why were there at least 2 times during the flight when the speed of the plane is 400 miles per hour? Okay, so now let's think about this logically. Ideally, the plane, when it takes off, it starts at 0 miles per hour, right? Now, at some point, it clocked 454.45 miles per hour. And then, of course, when it lands, the plane needs to go back to 0. So obviously, in order to get from 0 to 454, we have to pass 400, don't we? In order to get from stopped to 454 miles per hour, we have to travel at 400 miles per hour somewhere in between that. And then again, when descending or coming to a stop or whatever, in between 454 and 0, at some point again, I had to clock 400 miles per hour, or the airplane did. So, explanation. It's a little long. I'm going to write it out, and I'll let you write it. Okay, so the MVT guarantees a time c, where c is between 0 and 5.5 hours, right? Such that the average velocity was 454.545 miles per hour. Applying the intermediate value theorem, now this is a little bit older, but the intermediate value theorem is pretty much what I was explaining here, right? That in order to get to 454, 100 miles per hour, I have to pass 400 miles per hour. So applying the IVT, you see that there are at least 2 times during the flight when the speed was 400 miles per hour, because 400 is between 0 and 454. Once was on the way up, and then on the way down. All right, and that is it.